Hello everyone, welcome back again to this online structural geology NPTEL course, and we are learning rheology, and we are in the lecture number 12. We are the last lecture of rheology. We have learned elastic, viscous and plastic rheology. Then we have learned elastoviscous, elastoplastic and viscoplastic rheology. We also learned some of their applications in terms of structural geology and geodynamics. We will continue with the rheology throughout the lecture whenever we learn fold, fault, lineation, foliation. So, all these things we mostly learn in the context or light of rheology, along with their some other parameters. But this lecture would particularly focus on the role of external parameters in response to the strength and deformation of rock materials. This particular topic, that what is the role of external parameters in governing the flow or strength of the materials, you may not consider is a typical part of rheology or integration of rheological studies, but for rock deformation studies, for structural geology, these are very, very important, and therefore, I decided to include it in the course of rheology. Now, we will cover mostly 4 different important parameters. One is pressure, and then second one is temperature. After that, we will look at the pore pressure and strain rate. So, these 4 parameters and their influence in governing the strength and flow of rocks. Now, we know that pressure and temperature, as we go deeper of this earth, they do increase. Pore pressure is something which mostly applicable for reservoir rocks, where the porous spaces of the rocks are filled by either fluid, it could be water, it could be gas, it could be hydrocarbons, so on, at more or less shallow depth. And in deeper earth, it could be the melt in partially molten rocks and so on. So, the pore pressure has a very important role in determining the strength and flow of the rocks in general, because if I have a rock at say 20 megapascal confining pressure, then if I add pore pressure to the rock, the effective confining pressure reduces. We will learn about it later when we learn deformation mechanism, because pore pressure exerts an opposite force to the wall of the rock, and therefore, the total confining pressure reduces. So, we will see that how the pore pressure plays a role in governing the strength of the rocks. And then strain rate is also very important, because in the earth, though the process is extremely slow, but even within the range of slowness, there are many varieties, many ways, or many possible strain rates rocks do deform. So, pressure, temperature, these are extremely important on finding the behavior of the rocks under stress, and at the same time pore pressure and strain rate. So, we will look at these 4, and the expressions of these 4 terminologies or 4 terms or 4 external parameters in governing the strength and the flow of the rocks are mostly derived from experimental observations. So, there are many different ways of running experiments, which is not the part of this course, but something is very important to consider right now before we start the actual slides, where we will see the role of pressure, temperature, pore fluid pressure and strain rate. It is important to understand very clearly that there is no single equation or constitutive law to describe the flow or failure criteria of rocks in the wide range of physical conditions, and therefore, we had to have these different kinds of rheologies, and whichever fits with my observation, I will use it without breaking the laws of physics and science in general. And it is also important to understand the expressions of behavior of the rock, and the failure pattern, failure mechanisms are essentially different on the regime of the stress you are applying. That means, if you are in compressive domain, the behavior is different to that of tensile and shearing domain. And there is also one very important thing to remember, that if you are applying compressive stress, then the strength of the rock is much higher than the tensile conditions. So, all these parameters constitute, or all these statements are some sort of prerequisites in understanding the flow of rocks at different pressure and temperature. And talking about pressure and temperature, we know that at surface or subsurface conditions, the temperature is not very significant. We can go up to 200 maximum degree centigrades, 200 degree centigrades temperature. But at depth, we have much larger, much higher, much greater temperature. And the general observations from experiments or from the behavior of the rocks that we see frozen in the field, that effect of pressure is much more prominent at low temperatures. So, that is below 200 or 300 degree centigrades. Temperature does not play much role in governing the deformation of the rocks at low temperatures, but pressure, yes. But at higher temperature, in terms of rock deformation or rock rheology or deformation structures, temperatures are the key parameters. So, above 300 or 350 degrees, the effect of pressure is not that much when we talk about, or when we say this in the context of deformation structures and rheology. The pressure has some other effects, but deformation behavior is essentially governed by temperature at depth, and therefore at higher temperature regimes. So, based on these four ideas, we will now move to our findings on experimental findings. We learned that how the pressure, temperature, pore pressure and strain rate influence the deformation of rocks. The first one we take is confining pressure, and in all slides we will see this kind of curves, where the vertical axis is stress or differential stress, or the dynamic term which is related, which is plotted against a kinematic term, strain. And then what we see in this plot, the different curves. So, the sample was a crown point limestone that was deformed at room temperature at variable confined pressure. That means, the sample was taken to different pressures, different isostatic conditions, and then it was deformed. So, the isostatic pressure or confining pressure at variable, it ranged as low as 20 megapascals to 140 megapascals. You know what is the pressure conversion with the depth, and you can consider, or you can think that what corresponds to 20 megapascal, what depth it corresponds, and what depth it corresponds to 140 megapascals. If we look at all these curves, the stress versus strain curve at different confining pressures, where the temperature kept constant and the deformation rate as well, the strain rate, we see that it has an extreme variable behavior under stress. At low confining pressure, it goes to its elastic limit, and then it weakens, what we call strain weakening, we learnt in the last lecture. Then it does a little bit of strain hardening and flows steadily. Whether as 140 megapascals, it reaches its yield strength somewhere here, and then it flows steadily. So, deformation mechanism or flow behavior is different at different pressures, but this is not what we are going to look right now. What we see, that strength of this rock, the peak value of the differential stress at different confining pressures, this crown point limestone has achieved, has a relationship that with increasing confining pressure, the strength of the rock has increased, and this is more or less constant for any of the rocks we think of. So, in general, you can say that confining pressure increases the strength of the rock. Now, we can see it in a different way. So, this is another experiment on granite performed by Byerly. So, in this side again we have differential stress, and this side we have confining pressure, and we see that the strength of the rocks increased gradually, and in this case these are performed at different experimental conditions, maximum up to 1000, close to 1000 megapascals, and lower up to this may be 40 or 60 megapascals. So, in this wide range of experiments we see the strength of the granite that Byerly has used increased, and it got more or less increased non-linearly. So, the strength increase is not linear with confining pressure. Now, I must say here that most of the examples that I am going to cite are very old experiments, just to show some sort of my respect to all these great experimentalists and structural geologists who thought of running these experiments and contributed to our understanding. So, most of these experiments that we will see, these are pretty old publications, but they are very relevant today, and we also use it. There are many new experiments on a similar line, but to deal with a different problem. I did not pick them up, I picked the old ones, some way to show my respect to all these great scientists. Now, if we look at the temperature, and then again it is performed by Griggs in 1960, and this sample he used was basalt. So, in this case the confining pressure was 5000 megapascal or 5 kilobar. The strain rate was constant and temperature was variable. So, he wanted to check the effect of temperature on the strength of this basalt. So, you clearly see that at 25 degree centigrades the curve looks like this blue curve, and at 800 degree centigrades the curve look like this. So, here the peak strength is close to how much 1600 megapascal, and here it is probably 150 megapascal. So, 1500 megapascal the strength is reduced by raising the temperature from 25 degree centigrades to 800 degree centigrades, and this is remarkable. You can see it, and in between we see that temperature gradually decreases the strength. So, 25 to 300, 300 to 500, 500 to 700, 700 to 800, the strength or the flow stress of this basalt slowly decreased with the temperature. So, you can conclude from this plot that rocks have lower failure strength when you increase the temperature, or it flows at low pressure, low differential stress when the temperature is much higher. We can also see in a different plot, again these are pretty old work. One is this blue and orange. So, this one and this one, these are granodiorite rock, and rests are granite, westerly granite. These granodiorites were deformed with a strain rate of 10 to the power minus 4 per second, and the granites were deformed with the strain rate of 10 to the power minus 5 per second. And what we are plotting here, differential stress versus temperature, and the authors plotted the peak stress, the peak value. And you can see that the temperature from 0 to 700 degree centigrades here, if the temperature got increased, then at room pressure the temperature decrease, the strength decreases like that. At 50 megapascal the strength decreased like that, whereas in westerly granite when dealt with 400 megapascal confining pressure, the strength decreased again little non-linearly, but at 80 megapascal it was more or less linear. So, this kind of behaviors, this kind of relationships one can obtain, that okay, I change the temperature, but I observe it at different confinements. That means, at different depths if I increase the temperature, what is going to be the behavior, whether the strength change or flow stress change is linear or non-linear, and so on. So, this is another way of looking at the role of temperature together with pressure in governing the strength of the rock, but the conclusion or take home message from this plot is yes, the same temperature lowers the failure and flow stress or flow strength of rock. Now, let us look at the pore pressure. So, these experiments were done with a barrier sandstone and performed by again another great geologist, Handin. The paper got published in 1963. So, barrier sandstone is a sandstone that has a porosity, very consistent porosity from 15 to 25%. So, this sandstone typically has 22% porosity. The confinement was 200 megapascal. The experiments were performed at room temperature, and what Handin did, he varied the pore pressure. So, these values here at the bottom of the curve, these are your pore pressure values at 200 megapascal. So, when the pore pressure is equal to the confined pressure, so that means the rock is almost at room pressure, because 200 minus 200 comes to 0, close to 0. So, here we see that the strength is very low, right, this orange curve. But when the strength got increased from 200, when the pore pressure, he decreased from 200 to 150 megapascal, 50 megapascal decrease of pore pressure increased the strength of the rock. From 150 to further decrease to 100 megapascal, further decrease to 50 megapascal and further to 0 megapascal, we see that strength and flow of the rock has increased. So, pore pressure effectively lowers or decreases the strength of the rock. This was one of the first experiments where Handin showed this typical phenomena of deformation behavior. Now, this is another way of looking at how pore pressure does play the role in governing the strength or flow of the rocks. So, these are again done by porous sandstone, and this time the experiments were done by Murrell in 1965, and here the porosity was 21%. So, different circles here are of different confining pressures that applied, and in this x axis we have different pore pressure. So, what we see, for example, if I take this green circle where the confining pressure was 110 megapascal. So, at 0 pore pressure the strength was extremely high, close to 400 megapascal, but close to 50 megapascal pore pressure the strength reduces to 300 megapascal. So, increasing pore pressure is reducing the strength of the rock, and then probably at 75 or 80 megapascal pore pressure it further reduced, and again it further reduced when the pore pressure got increased, and this is obvious for all other values, but at different confinement. But the take home message again from this plot is that pore pressure reduces the flow and failure strength of rocks. Now, let us have a look of this very important series of curves where we are going to see that what is the effect of strain rate, deformation rate, that means how fast the rocks are being deformed. And these experiments again performed by another one of the great experimentalists, Hurd. It is a paper in 1963, and he worked with Yule marble. The confining pressure was 500 megapascal and temperature was 500 degrees centigrade. So, these two were kept constant, and he varied the strain rate from 4.0 to 10 to the power minus 1 to 3.3 into 10 to the power minus 8 per second was the strain rate. So, clearly we can see that from here to here strain rate is increasing. So, with the magnitude here is 8, then 7, then 6, then 5 and so on. So, with the order of magnitudes one can change in an experiment, and this is how the strain rate has increased, and clearly from all these curves we can see that with increasing strain rate each and every step the flow strength or flow stress of this rock, this Yule marble has increased. So, we can conclude that strain rate increases the failure strength. Now, one term is written here at higher temperature. So, this is possible only at higher temperature. If you increase the strain rate, the strength increases, and this is probably due to the viscous behavior of the rock. So, you achieve viscosity and therefore, you increase the strength. But at room temperature or at low temperature, people run experiments. Again, these are pretty old experiments, but here we see that increasing strain rate, with increasing strain rate, the strength of the rocks are not increasing the way we saw with the Yule marble. For example, we can consider another marble, which is a very famous marble that people use for experiments, is Carrara marble. Here, the strain rate got increased from the order of 10 to the power minus 7 to almost 10 to the power minus 2, and the flow strength was more or less constant. So, strength at low temperature is not a function of strain rate. So, strain rate at high temperature, it increases the strength, but at low temperature it hardly has any influence in the deformation of the rocks, and this is most likely because at low temperature rocks do behave in elastic manner, and elasticity we know does not depend on strain rate. But we still see with some granites, for example, this is Indian granite and this is a kind of shale where it is increasing slowly even with Carrara marble, and this is because these rocks are not ideal elastic material. So, it has some sort of other components of the rheology, maybe viscous, maybe plastic a little bit, and therefore, the strength do increase, but it does not increase the way we saw with the Yule marble in the previous slide. So, these role of pressure, temperature, pore pressure and strain rate in determining the rheology of the rocks are extremely important, and we will see when we see the real examples of structural geology, when you go to the field, when you learn about fold, fault, their applications and so on. These things are extremely important. So, keep this in mind. Now, in the next lecture, we are done with this lecture. In the next lecture, we talk to a different, we will cover a different topic. So, we learned that what the effect of rheology on the deformation of the rocks. This is what we have to learn. We learned strain, we learned stress, we learned their relationships, that what are the different possible ways a rock can deform. But what is the response of a rock when it is deforming in viscous manner, when it is deforming in plastic manner, when it is deforming in elastoviscous manner, when it is deforming in elastoplastic manner, that what are the expressions of the rock. And I tell you, like we say that drops of water makes an ocean, very similarly most of the deformations initiate at the crystal scale, at the very minute scale. So, either it nucleates at a single point and then it propagates to make it a very large event, or many little events do nucleate at different places, they coalesce and they form again a very large event. So, how does it happen? That what are the typical structures we produce under different rheological domains, how they are produced, and most importantly, if they are produced, they stay as they are or they change with time. And we will answer all these questions in the next lecture with the deformation mechanisms of rocks. Thank you very much.